talk now a little bit about what the effects of alveolar air are on the rest of the body. Gas transfer at the alveoli and at the tissues. Okay, so here's our alveoli. Here's the blood coming to them. So if the blood's going this way, what kind of blood vessels are these heading toward the alveoli? Systemic or pulmonary? If they're heading toward the lungs, they are pulmonary. If they're heading toward the lungs away from the heart, they are arteries or veins.
Arteries.
Away from the heart is arteries. So these are pulmonary arteries. So that makes these pulmonary veins. Down here, we're going to have the body tissues. Everything in the body except the lungs, all grouped together. So, we've got stuff coming to it, stuff coming to the tissues of the body. Systemic or pulmonary? Systemic. Now everyone's afraid to answer. Heading away from the heart toward the tissues makes it arteries or veins?
Arteries.
Or both. Okay. Away from the heart,
Arteries.
arteries. Which makes these heading away from the tissues toward the heart,
Veins.
systemic veins. Which makes this and this the heart. Let's see, the side of the heart that receives from the systemic veins and goes toward the pulmonary arteries, left or right? Good. Right side of the heart, left side of the heart. Okay. Now, I told you that the PO2 in the alveolar air is typically about 100, and the PCO2 is typically about 40. Oh, and just so you know, do you remember how many alveoli I told you were in the lungs?
Approximately 1 million.
Yeah, so just the other day, just for the heck of it, I decided to check on that. Say, okay, so what's the surface area of one alveolus then, based on its size? And if I have 1 million of them, how much surface area is that? It should be about 70 square meters, right? That turns out to be about 0.2 square meters. So I did a little more looking. Turns off my estimate of 1 million per lung is off by a factor of approximately 450.
Nice.
It's actually about 450 million alveoli, just so you know.
Oh my god.
Oh
My bad.
God.
Yeah, just a minor error there. So you have the right number. We're talking total, yeah, about 400, about total between both lungs, about 450 million, although people vary in their estimates, alveoli. Anyway, so mea culpa. Now, if the blood that passes through these pulmonary capillaries reaches equilibrium with this air, and this air isn't changing because we are breathing, what should the PO2 and PCO2 of the blood coming away from the lungs be?
The same.
It should be the same. PO2 of 100, PCO2 of about 40. As I go through the heart, those numbers do not change significantly. The blood passing through the chambers of the heart is not exchanging gases into any significant degree with anything, maybe the endothelium, not enough to change it noticeably. So when I come out of the heart, nothing has changed. And now I approach the systemic capillaries. And I want to know which way is our oxygen and CO2 going to be going. In order to know that, I need to know the PO2 and PCO2 of the extracellular fluid in the body tissues. The because that's the material that the blood is going to be exchanging with. ECF to blood plasma, or the other way. Now, the problem is that is not a constant in the body. For example, the hard-working muscles in your limbs will be using up a lot more oxygen than, say, adipose tissue in your abdomen. So the PO2 and PCO2 of body tissue varies a lot. However, as a rough average of the body, you might have a PO2 of about 40 and a PCO2 of about 47.
The book uses 46.
Sorry?
The book uses 46.
I like mine better. It's a prime number, isn't it? 47? It's a prime. I like prime numbers. We'll go with 47. To be perfectly honest, if on a test I said, what's the PCO2 of body tissue, and you said 46, it's fine. It's a reasonable estimate. I wouldn't give you a multiple choice question. It's like 45, 46, 47, or 48. Except now that you've said that, maybe I'm down there. So, as we pass through these capillaries nice and slowly, we will be reaching equilibrium with the tissue ECF. So what will the PO2 be over here? So you're saying it's going to match the tissue. We said it matched here because we were breathing, so these numbers didn't change. Why wouldn't these numbers change? As I give oxygen to this tissue, why doesn't this number go up? What's the tissue doing with the oxygen?
It's using it for energy.
It's using it up, yeah. So in theory, I'm delivering oxygen to this tissue at the rate at which it's using it. So this number should not change much. Therefore, I come away matching the tissue.
Say that one more time.
So up here, we agreed that it wouldn't change the air because we're refreshing that air.
Yeah.
So down here, the question was, as I deliver oxygen to the tissue, why doesn't the 40 rise so that I reach some number between these two? And the answer is, the tissue burns the oxygen.
Oh.
I'm delivering O2, hopefully, at the same rate that it's being burned.
Okay.
Meaning, and I'm taking CO2 at the same rate it's being produced.
Okay.
So these two numbers shouldn't change much.
Okay.
And so we go back to the heart. And come out about like that. So as we go through the lungs, which way is oxygen going to go? Air to blood or blood to air? Here's the blood coming in, PO2 of 100, PO2 of 40. Which way does it go? Air to blood. So oxygen enters. How about the carbon dioxide? 47 to 40.
Leaves.
Here in the tissues, oxygen 100 versus 40. 47 to 40. That's gas delivery in a nutshell. Also notice when we talk about deoxygenated blood in the systemic veins, it's not actually deoxygenated. For reasons we'll get to that you can't directly predict from this right now, it actually has about 3/4 of its oxygen. But we'll get to why I can say that we'll hopefully get to it tonight. Now, one other thing to keep in mind. Notice, I lose 60 millimeters of mercury of oxygen, and I pick up 7 of CO2. Doesn't that seem asymmetrical? Shouldn't oxygen be being consumed and CO2 being produced at about the same rate? They should be, roughly. The basic equation of metabolism is 6 O2 go in, 6 CO2 come out.
Yeah.
They should be at least reasonably close. Here's where, remember, that idea of solubility comes in. A change in the PO2 of oxygen and the change in the PCO2 in PO2 of oxygen. A change in PO2 and a change in PCO2. Do not try to interpret from that how much oxygen or CO2 has moved, because it depends on their solubilities. All I'm trying to get here is, if you're looking at this and wondering why we seem to be giving up so much more oxygen than we're picking up of CO2, that's not how partial pressures work. That going from 40 to 47 may represent a lot more CO2 than it looks like.
Oh, that's right.
Yeah.
No, because it's not the concentration.
It's not concentration. CO2 rests more easily. And there are even a few other issues which we'll get to next lecture. Because not all the CO2 that you put into blood plasma stays as CO2. A A lot of it goes through certain reactions to other stuff. All right, so this is our general map of how PO2 and PCO2 change between alveoli tissues and the rest of the blood vessels. What I want to now go to is talking about what happens with the oxygen in the blood. We'll get to CO2 next time, but it's important that we talk about oxygen. We may not even finish it because there's some interesting stuff to discuss. I've always wanted to develop a magic trick I could use to show about oxygen. It would work something like this, that I'd put a petri dish with a little sponge in it here. And I'd have a big pitcher of water. I'd say, I will pour this water into this petri dish without it spilling. All of it. And you would say, ha, Dr. Rad, even you could not do such a thing. And then I would do it. Pour the water in, and it pours in, and it just disappears. And the petri dish fills, but very, very gradually. And I would say, that is how oxygen works in blood. You would say, brilliant. So, but let's talk about what that would mean. Let's imagine we are blood circulating through the pulmonary capillaries. So, here's my alveoli. Has a PO2 of about 100. Now here, I'm going to make the blood a lot more complicated. And right now, you can write this part down, but then don't write anything else down for a moment. Just listen and watch. Let's pretend for a moment that we have no red blood cells and no hemoglobin. We're just using blood plasma. So the PO2 of my blood plasma is 40. So as this blood plasma comes around, which way is oxygen going to go? Yeah, I agree. I'm going to represent this with a series of little boxes. Isn't that a Pete Seeger song? Little box. Anyway, we're going to say each box represents 20 millimeters of mercury. Okay, so there's 2 of those filled. Now, as I come along here, oxygen starts moving from air to blood. So here's my boxes. They had 2, 3, 4, 5. Now I have a PO2 of 100. These are now at equilibrium. We agree? So we come away. And a PO2 of 100. So far, so good. The problem is, plasma doesn't hold very much oxygen. Plasma holds about 10% of your oxygen needs. If all you had was blood plasma, you would be about 90% short on oxygen storage. You'd be dead in seconds. So, we need a way to make this blood able to hold a lot more oxygen. That's the job of hemoglobin. Hemoglobin is that protein you find in the red blood cells, about 250 million per cell. Each one is 4 subunits, each of which has a heme group with 1 iron. Each iron holds 1 O2 molecule. So a hemoglobin can hold 4 oxygens. Good? Okay. Now, in the blood, I'm going to kind of divide up the blood between plasma and hemoglobin.
Are we still not drawing, just paying attention?
I would still not draw it just for the moment.
Okay.
I have a quick question.
Go ahead.
You said each hemoglobin can hold 4 oxygen. I thought it was each heme group can hold 4 oxygen and each hemoglobin has 250
No.
million.
Each red blood cell has 250 million hemoglobin proteins.
Okay, then, okay.
Each protein has 4 pieces.
Yeah.
Each piece has a heme group. Each heme group has an iron. Now, here's our question. Hemoglobin can hold up to 4 oxygen. How many will it hold at any given moment? How many does it grab onto? Will it hold as many as it can? hemoglobin is complicated. It's actually kind of a lovely mechanism how it works. I have a weird analogy I use to help students understand this, but it is a really, really weird analogy. Would you like to try it?
Sure.
Go for it.
All right. I want you to imagine that you are a four-armed mutant human. So 1, 2, 3, 4. 4 arms. We are going to be walking around in a room full of hundreds of thousands of little super bouncy balls, bouncing all around the room. Good so far? Okay. You folks are good at this by now. You're like, sure, Dr. Red, whatever. Okay. So here we are. Now, super balls may bounce into my hand. I like super balls to some degree. So when one hits my hand, I have some tendency to grip it a little bit. But it can also bounce out of my hand. They don't stay forever. Okay, we good so far? So now here's the other weird thing about us as four-armed mutant super ball-loving creatures. We normally walk around kind of like this, with our arms folded up, so it's fairly hard for a super ball to get in there. But as super balls bounce into our hands, we tend to relax a little, making it easier for super balls to come to us. The more I'm holding, the more I tend to be open to holding them. The fewer I'm holding, the more reluctant I am to grab them. Okay? So now, here's what we're going to imagine. Here I am, I'm going to walk in the room with no super balls. It's not that I can't grab them, I'm just kind of pulled inward. Now, let's assume there's a lot of super balls in here. So I walk in and immediately, pop, one of them bounces into this hand. So I go, whoop, and since there's a lot of them, boop, another one. And before I drop one of them, a third one. And then maybe even a fourth one. Every once in a while I drop one. And when I drop them, I come in a little bit. But since there's so many, another one is likely to come into that empty hand. So we're all walking around like this, and someone takes a picture, and they count how many balls each of you is holding. How many would they count on average, do you think?
2 to 3.
Okay, people are saying 2 to 3. Kind of depends on how many there are and how quickly I do this. Let's say there's a lot. So whenever I'm mostly walking around like this, and whenever one comes out, another one is very likely to come in quickly. 3 to 4. Maybe on average 3.9, 3.8 if we added them all. You get the idea? All right. Now imagine that I use my big vacuum cleaner and suck 90% of the super balls out of here. So now there's very few. So here I am walking around holding 3 or 4, and I drop one. So my other arms come in. Now, it's now much less likely that another one will come in. We agree? So it's more likely I'm going to drop another one. And maybe another. Now, there will come a point at which the number that are in here are coming to me and holding at the same rate at which I'm dropping them. I'll reach equilibrium with this, but I'll be holding fewer when I get to equilibrium. So now we're wandering around and someone takes a picture and now they see maybe 1, 2, depends on how few there are. This depends on the fact that my likelihood of catching a new one depends on how many I'm already holding. If I'm already holding 3, I'm likely to catch a 4th. If I'm only holding 1, I'm less likely to catch another one. So I change my affinity, is the word we use, for super balls based on how many super balls I'm holding and how many are around me. The more there are, the more likely I am to be holding them and the more I will tend to grab more. Make a little bit of sense? Okay, now let's bring that into hemoglobin. Here, there aren't many super balls in that room. So the hemoglobin is probably not holding very many. Now, as it turns out, hemoglobin is fairly eager even at this point. So I'm just going to give you this number right now. This is nothing you can come up with. Each hemoglobin is holding, on average, 3. Notice I've drawn one with 2 and one with 4, but on average 3. Good? Okay. Now, bring the same stuff in here. One of the reasons I didn't want you to draw this is because we're about to do this sort of as a little animation. I'm going to suggest that when I finish this, Then you figure out how you want to draw it for you. We'll take a little time. So, I'm going to step back a step before this has really started. Let's put our hemoglobins the way they were. Okay. Now, oxygen starts to come in to the blood plasma. More superballs in the room. What does that do to the tendency of hemoglobin to grab onto oxygen? Yeah, it makes it more likely that they're going to happen to bounce onto it, which makes it a little more open to it. Where does it get the oxygens that it binds? From the plasma. That's one of the key things to realize. Okay, so now I can take another one into the plasma, right? And the hemoglobin says, oh good, more. As oxygen is entering the plasma and the plasma PO2 is going up, the hemoglobin becomes more eager to take it from the plasma. Before the hemoglobin, how many did we take total? How many boxes did we fill? 3. Boop, boop, boop. We were done. Now we bring one in, goes to the hemoglobin. Bring another in, to the hemoglobin. Another one. Gradually, these are going to fill up. But the hemoglobin just as they fill, the hemoglobin keeps sucking more out of the plasma. So these are now filling up very slowly, and by the time this fills, the hemoglobin is going to be almost completely full. So how many did we get? A lot more. As we filled the plasma, the hemoglobin made room in the plasma so more oxygen could come in. So we ended up taking a lot of oxygen out of that air. This is the key to hemoglobin. As you put more oxygen in the plasma, the hemoglobin becomes more ready to take it from the plasma, giving you more room to bring more in. Yeah. These represent the plasma, with each block representing 20 millimeters of mercury. Notice how much more oxygen we can store here than here. And that actually understates it by a lot. Hemoglobin can store something like 35 times as much as the plasma can. There is another weird analogy for this one. This one involves you and your little sibling going to the candy store. So, your little sibling goes to the candy store with a very small bag. You go with your giant sack. But you're far too cool to be seen taking candy from the store. Don't shop for candy. Grown person. Your little sibling has no such compunctions. Now, if you weren't there, they go in and they say, candy, 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 sack's full, done, they leave. While you are too cool to take candy from the shelves, you are not too cool to steal it from your little sibling. So, your sibling comes in and says, candy, and you say, candy. Your sibling says, wow, I've got more room, candy, and you say, candy. Now, you're not a monster. You're not going to drain their little bag entirely, but as it fills up, you figure you have a tax kind of going on here, and so you're just going to keep taking it. And there will reach a point as their bag gradually fills, and it's gradually because you keep taking it away. As your bag fills up, so will theirs. And you leave the store with them full and your bag full. You are the hemoglobin, they are the plasma. Your willingness to take from them depends on how full their bag is. The more full it is, the more you're willing to take. Make some sense? Yes, that is the key point. Hemoglobin's affinity for oxygen depends on the amount that's in the plasma. The more that's in the plasma, the higher the hemoglobin's affinity.
So will hemoglobin, is there a tendency for the hemoglobin to eventually deplete plasma completely as O2?
It can't, because if it did, if the plasma PO2 dropped enough, hemoglobin's affinity would drop. And it would start giving oxygen back to the plasma. You get to the point where they're in equilibrium. And there is a relationship. We can say, for this plasma PO2, hemoglobin will tend to be this saturated. So there's a graph. Of course there's a graph. There's always a graph. You know it's science when there's a graph. This is one of the more important graphs. This is the hemoglobin oxygen dissociation curve. I know it's a great name.
And we're still gonna get time to do our version of the German.
Sure. Mostly what I want you to do is think about how are you going to draw this in a way that makes it make sense to you. This one you should write down. This is the hemoglobin oxygen dissociation curve. This tells you for a particular plasma PO2, for a particular amount of oxygen in the plasma, how eager is hemoglobin to bind to oxygen, as measured in how saturated will the hemoglobin tend to be. 100% saturated, in other words, each one has 4. 50%, on average they have 2. So, in the blood that's in my systemic arteries, where the PO2 is 100, for those of you who've ever worked in a hospital, what's the correct oxygen saturation to see in systemic arterial blood in a healthy person?
92 to 100.
Sorry?
92 to 100.
92 to 100. And it's on average, for hemoglobin at a PO2 of 100, should come out to about 98%. Hemoglobin has in most people has an affinity of about 98% for oxygen when the PO2 around it is 100. Which means when the plasma has a PO2 of 100, if you had 25 hemoglobin molecules, which means 100 irons, 98 of them will have oxygens. Won't always be the same 98, it goes back and forth, but about 98 of them will be full. It's about as full as it can get. This is one reason, by the way, why if you breathe oxygen, it doesn't actually increase the amount of oxygen stored in your blood very much. Because your blood is already storing almost as much oxygen as the hemoglobin can hold. If you breathe pure O2, your plasma will get more oxygen, but that's not that much more oxygen measured in actual amount. It still has effects, but all right. So let's see, my plasma PO2 here is 100. As it goes to here, as we go through here and the plasma PO2 drops as oxygen moves to the tissue, what do I think the hemoglobin should do? Should it release its oxygen at this point? As we're going through here, we want that hemoglobin to give its oxygen up to the plasma so it can pass on to the tissue. We want its affinity to drop, and it does. By the time plasma PO2 drops to about 40, hemoglobin's affinity drops to about 75%. So what I'm telling you is that as this blood passes along here, and the PO2 drops from 100 to 40, hemoglobin will go from about 98% saturated, in other words, each of them is holding 4 oxygens about, to 75% saturated, each of them is holding about 3. Usually the response is, so you're telling me my hemoglobin gives up 1 of its 4 oxygens to my tissue? And the answer is yeah. On average, over the body, yeah. Venous blood is still about 75% saturated with oxygen. Doesn't that seem wasteful? No, because some tissues use a lot more oxygen. Hard-working muscle might have a PO2 of 20. At a PO2 of 20, hemoglobin affinity drops to about 35%. So suddenly the hemoglobin starts saying, okay, and surrendering the oxygen rapidly.
Is that because the affinity for it is lowering?
Yes, because it actually mostly happens between about 40 and 20 hemoglobin's affinity starts to change rapidly, just because of the way the hemoglobin is made. It only drops a little up to here, about 1 out of 4. But between 40 and 20, it'll drop about almost 2 more on average. If you actually plot out the full curve,
So at that point, you've given up 3 and you have 1.
you've given up a little less than 3 on average. Most of your hemoglobins will have 1, some will have 2. There'll be a scattering of 0s and 3s.
So at around 20 will be at 35?
Yeah. This is the hemoglobin oxygen curve. This tells you a lot of useful stuff about hemoglobin. This tells me that if my venous blood, the blood in my systemic veins, has a PO2 of 40, I expect it to be about 75% saturated. And as I move it into the lungs, where it's exposed to, where it becomes a PO2 of 100, the hemoglobin will take on oxygen until it reaches about 98% saturation. If I then move that out into the tissues and the PO2 starts dropping, the affinity of the hemoglobin starts dropping and it starts surrendering its oxygen back to the plasma.
Then what's the reasoning for it being 40, if it's blood plasma O2 is at 40, and then it's still at 75%? If the hemoglobin is not likely to hold on to it, like oxygen's always bouncing in and out of it, it's not really holding on to it, then why is it more likely to hold on to it than not?
It's not, to say that it's just bouncing around and not holding on to it is a little overstated. This is a measure of how much it's holding on. If it would help, you can think of it as our forearm people walking around. Imagine that they leave their hands out like this all the time, but it's how tightly they grip. The more of their hands are full, the harder they hold on, the less likely it is for them to drop it, if that helps.
Yeah.
It's also not a coincidence that the slope gets steep right here. This is the approximate range of PO2s you find in your tissue. So when a tissue goes from being not too oxygen hungry to very oxygen hungry, the hemoglobin goes from still fairly tight to very generous. Works out very nicely that way. Yes?
For that 20, where is that in this slide? In veins?
It's not shown on here,
Okay,
but this is just a rough average of the body.
yeah.
Stuff like adipose tissue might have a PO2 of 60 because it doesn't use much oxygen. Hard-working muscle that's in active use, might have a PO2 of 20. So this is just the average over the whole body.
Okay.
This is what you might measure in, say, the vena cava, where you've got a mix of blood from all over the body coming back.
But if you measure it on, you said,
If I took a vein
adipose?
let's say if I took a vein coming back from my quadriceps muscle while I'm doing my best to run, which is not well, I would measure a lower PO2 and a lower saturation than I would coming back from elsewhere. That tissue is pulling more oxygen from the blood, making it more desaturated.
But the closer it is to the lungs, the higher it is.
Not exactly, because it doesn't actually start getting more oxygen back until it gets to the alveoli.
Okay.
The blood going into the lungs looks like that.
But you could also find some that look like a...
At that point, it's a mix, so
Yeah.
no, it's all mixed together, and it's about 40 overall. Yeah.
What about places like the brain? Doesn't that need to have oxygen?
It's kind of funny how the brain works. It does have a high oxygen demand, but it doesn't vary all that much. So I don't know off the top of my head what the numbers are, but I'm guessing it's not too far from the body average. And it doesn't change all that much over different conditions. That may be sleep. Questions? Okay. You'll want to know this, you'll want to be able to reconstruct this curve. You can do it with those 3 numbers, but more importantly, you will want to be able to interpret it. If I said, what hemoglobin saturation would I expect to see at a plasma PO2 of 60? You'd want to be able to go, I don't know, about 85, something like that. Or if I said, I'm looking at blood with a PO2 with a saturation of 40%. What's the PO2 probably? you'd say 40% is about here. Yeah, maybe 23, 25, something in there. I'm not gonna ask you for a precise number, obviously, because, yeah, but if your multiple choice answers were 0, 25, 50, and 75, 25 is clearly the right one. Yes?
What is the name of that chart?
The hemoglobin oxygen dissociation curve. So if I did the magic trick, what it would be is my petri dish with little sponge is connected to a very big sponge under the desk. So as I pour water into the petri dish, it goes into the sponge and then gets sucked into the bigger sponge. What does the bigger sponge represent?
Hemoglobin.
Hemoglobin. And the petri dish represents plasma. The idea is, as I add oxygen to the plasma, it gets taken into the much larger hemoglobin storage. Now is a good time to try to figure out how you're going to write this. Because now is a good time to end lecture. So, tell you what, I'm going to sit here for about 5 to 10 minutes while people work on this, and if you have questions, you can ask to help you